Number one is an expected value problem, but there's a missing probability if you look in that table. We don't know what the probability is of having one imperfection, but since you have the rest of them, you can get it, because all the probabilities have to add up to 1. So basically what happens is if you add up all the other probabilities that are there, find that sum and subtract it from 1, that has to be the probability that x equals 1. So if you do that, you end up with that the probability that x equals 1 is 0.37. Once you get that, you can find the expected value. In this case, finding the expected value ends up being fairly straightforward because the variable's probability distribution is already set up in table form. So once you have that 0.37, you essentially just cycle through the table. If you go column by column, you'll have 0 times the probability that x equals 0, which is 0.41, plus 1 times 0.37, plus 2 times 0.16, and so forth, just setting up the expected value using the formula for it, the general formula for a discrete distribution. And what you should end up with when you simplify all of that is 0.88. Number 2 is pretty similar to number 1. It's another general discrete expected value, except that unlike number 1, number 2 doesn't have a table. Number 2 does have the probability distribution, but it's essentially written out in that first sentence. So there are 2 possible values, making $4,000 or losing $1,000, and they have associated probabilities. So if it helps, which I think it will for a lot of people, you can make the table like the one that exists in number 1. The one for number 2 is a little bit smaller because it only has 2 possible values, and the other thing you have to watch out for is that the loss of 1,000 should be negative 1,000, not positive 1,000. With those things in mind, the table is behind me. It's really short, and once you have that, it turns into the exact same thing that you do in number 1. So that's what you should end up with. You get your 2 possible values, the making $4,000 and losing $1,000, and really just be careful about that losing $1,000. If that needs to have a negative sign, you should end up with an expected value of 250. We went over what the wrong answer would be in 3A, that it would just be treating the combination like it was division, and you get 9 divided by 3, which is 3. That is the most common wrong answer, and typically what you will get if you do that is a number much smaller than what the correct answer is, and that's exactly what happens here. So what I have behind me is I have the combination expanded out into factorials. Then you can expand the factorials out if you want to, but I would suggest following along with the way that we were doing it in class on Thursday and trying to get rid of the big factorial in the denominator right away. So that's what I've got up there. I'm going after that 6 factorial because 6 is bigger than 3. But for this one, I'll write out the entire factorials all the way. So 9 factorials, 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Then in the denominator, 3 factorial is 3 times 2 times 1, and then 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. There, with the factorials expanded out all the way, you can see the 2 6 factorials. They're right on top of each other. We can get rid of those. Then, is there anything else that we can do? Well, 3 will go into 9 3 times, 2 will go into 8 4 times, so what you end up with is 3 times 4 times 7, and that's really all that's left because at this point you've canceled everything out in the denominator, so it's 3 times 4 times 7 divided by 1, but 3 times 4 times 7 is 84, and that is the answer. That's 9 choose 3. Number 4 is 16 choose 11. Similar concept. Expand the combination out into factorials and then get rid of the big factorial in the denominator first. So this will be 16 factorial divided by 11 factorial times 5 factorial. And 11 is bigger than 5, so I'm going to get rid of that one. I'm not going to write out the full expansion of these factorials because the 16 factorial and the 11 factorial are kind of long. So what I'm going to do is I'm just going to write the 16 factorial as 16 times 15 times 14 times 13 times 12 times 11 factorial, and then just cancel those out. So you'll end up with 16 times 15 times 14 times 13 times 12 times 11 factorial in your numerator. And then in the denominator, I'm just going to leave the 11 factorial alone because I'm going to cancel it right away. but then I'm going to expand the 5 factorial into 5 times 4 times 3 times 2 times 1. Because then at this point, if I'm going after that big factorial, I can say, there's an 11 factorial, there's an 11 factorial. That's all multiplication, so there's nothing wrong with doing that. And then we'll just see what else we can do. So let's see. 5 and 3, when you multiply those, you get 15. So okay, 5, 3, cancels with the 15. Then other than that, 4 times 2 is 8, which would go into 16 twice. And now everything in the denominator is gone. Everything's canceled out. So what we're going to end up with is 2 times 14 times 13 times 12, which ends up being 4368. That's what you should get for 16 choose 11. 5, 6, and 7 on the back are binomial probabilities. And looking at number 5, 70% of the customers order coffee with dinner. So there's our P. It's going to be 0.7. And if 12 customers are randomly selected, it looks like that's going to be our N. So the experiment that's being repeated is to select a customer randomly and then to see if they ordered coffee with dinner. So this is going to be a binomial probability with N equal to 12, P equal to 0.7, and we want to find the probability that 9 customers order coffee with dinner. Okay, so that's going to be the probability that X equals 9. Substituting into the formula, that should be 12 choose 9 times 0.7 to the 9th power times 0.3 to the 3rd power. Like that. And then we'll be able to simplify that combination a little bit. That's going to break down, if you expand it into factorials, as 12 factorial over 9 factorial times 3 factorial. So with the usual strategy of trying to get rid of the big factorial first, you're going to try to get rid of that 9 factorial. Okay. If you want to write it out the really short way, which I'm going to do here, then if you want to mentally cancel out that 9 factorial, then what you'd be left with on the top would just be the first 3 things. Everything before you get down to the 9, right? So you would have 12 times 11 times 10 times 9 factorial, but if you're mentally canceling out the 9 factorial, you would just think of it as 12 times 11 times 10, and then you would end up with just the 3 factorial on the bottom. So 3 times 2 times 1. Then you're going to have the other stuff, the 0.7 to the 9th and 0.3 to the 3rd. So here, with the combination, I canceled out the 9 factorial already. I just don't have it written in. If you want to have that as an intermediate step, I guess you'd have the 9 factorial right there in the numerator, and then you'd have one in front of that 3 factorial. That's fine. So I just did it to kind of save a step and to make this part a lot smaller when it was written out on the board. But at this point, it's still the same kind of strategy. Is there anything that we can cancel? Yes, 3 times 2 is 6, which goes into 12 twice. So we can do that, and it looks like that combination is going to simplify to 220. So the probability that X equals 9 would be 220 times 0.7 to the 9th times 0.3 to the 3rd. So what you get for the probability that X equals 9 is 0.2397 if you round off to 4 places, which I would probably advocate because if you don't round off, this thing is going to be really long. Number 6, the one about the tax returns and whether or not they contain errors. Here the experiment that's being repeated is to randomly select a tax return and see if there are any mathematical errors on it. So the first thing that you want to find out is the expected number of returns containing mathematical errors. Well, here I suppose X being the number of returns containing mathematical errors, this is binomial, so you don't have to do it the long way. I suppose you could if you really felt like it, but that's a lot of work here. That's 21 individual probabilities. So we'll just do it like this. Since it's binomial, that will work. Generally, that won't work. It won't work for all discrete variables, but binomial ones it will. And here, that's going to make this really fast, because this is just going to be 20 times 0.15, so it's 3. That's it. Part B, we want the probability that exactly 2 returns contain mathematical errors. So this is a binomial probability. So if we follow along with the formula, this will be 20 choose 2 times 0.15 squared times 0.85 to the 18th power. Okay, Well, then we have to simplify 20 choose 2. So if you wrote that out in factorials, it would be a 20 factorial in the numerator, and then the denominator would be 2 factorial times 18 factorial. So you're going to get rid of that 18 factorial. You're not going to have a whole lot left after you do that, in the numerator or the denominator, I suppose. So the probability that x equals 2, if you do that, and I'll kind of write this one out the same way I did it in number 5, where I'll kind of mentally get rid of that 18 factorial and say, well, if you did that in the numerator, you would just have the things in front of the 18 left. So just the 20 and the 19. And then in the denominator, you're just going to have 2 factorial, which is 2 times 1. And then you'd have 0.15 to the second power and 0.85 to the 18th power. And then you could cancel the 2 with the 20 and say 2 goes into 20 10 times, so it looks like the combination ends up being 190. The probability that x equals 2 then is going to be 190 times 0.15 squared times 0.85 to the 18th power, and that ends up being 0.2293 if you round that to 4 places. So the probability that x equals 2 ends up being 0.2293. Number 7, also a binomial probability. Now the probability of a success is pretty low, since here a success would be defined as a vial having type AB blood in it. We expect the probability of success to be 4% based on what the percentage is for the population in general. Okay, well then the first thing that we're supposed to get is the probability that no samples contain type AB blood. That's going to be the probability that x equals 0. Okay, well then we can follow along with the formula. This one will be pretty fast, because this is going to be 15 choose 0 times 0.04 raised to the 0 power times 0.96 to the 15th power. But anything raised to the 0 power is 0, right? That's just an algebra thing. And then here, 15 choose 0 is 1, because this is a case of how many different ways could you pick 0 things out of 15? 1. You don't pick any, and that doesn't have any other arrangements. You can look at it that way. If you want to rewrite that with factorials, what you're going to get is 15 factorial divided by 0 times 15 factorial. The 15 factorials are going to cancel, and then 0 factorial by definition is 1. So you'll get that 1 as the simplification of that combination one way or another, either kind of working through it logically, or if you do it algebraically with the factorials, you're still going to end up in the same place. Either way, that's a 1. So the probability that x equals 0 is going to be 1 times 0.96 to the 15th. So really that's just 0.96 to the 15th. And what that works out to be, at least to 4 places, is 0.5421. So a fairly large probability, but that's because the probability of success in a single trial is so small. In part B, the thing that we're supposed to get is the probability that at least 2 samples contain type AB blood. If you do this directly, it will be far longer than if you do it using the complement. Because if you do it directly, you're going to need the probability that x equals 2, probability that x equals 3, 4 and 5 and 6 and 7 and 8, all the way up to 15. That's a lot of work. Or you can say, well, what if I try the complement? Is that going to be shorter? Yes, it is, because that will involve only 2 probabilities. You already have one of them. So I'm going to rewrite this as 1 minus the probability that x is strictly less than 2, because any possible value for x would either have to be greater than or equal to 2 or strictly less than 2, and those two inequalities don't overlap at all. So we can do this. So this was effectively using the complement, or using the idea that this probability plus this probability would have to add up to 1, except if we're going to get this one instead, we're going to do a whole lot less work. Because the only possible values that satisfy this inequality of being strictly less than 2 are 0 and 1. So the probability that x is greater than or equal to 2, we can rewrite as 1 minus, and I'm going to put this in brackets, the probability that x equals 0 plus the probability that x equals 1. And this one right here, we already have. So really at this point, we just have to go and get this one, the probability that x equals 1. So I suppose I have to kind of write it down here on the board, and then I'll go back and put the answer in up there. Okay, So I guess I can do this indented a little bit. So the probability that x equals 1, hopefully the glare doesn't get in the way too much, but let's see. It's hard for me to tell from this angle. So the probability that x equals 1 would be 15 choose 1 times 0.04 to the first power times 0.96 to the 14th. 15 choose 1 is going to be 15 because how many different ways could you pick one thing out of 15? There are 15 of them. You'll get that if you simplify it with the factorials as well. So this is 15 times 0.04 times 0.96 to the 14th. And if you simplify that, the probability that x equals 1 should end up being 0.3388. So that's an intermediate answer right there, that you need that piece up there. So that's what we're going to do with it. All right, so now we have that, and we have the probability that x equals 0 from part A. So now we can do this, which is ultimately what we're trying to get. This will be 1 minus, and then I guess I'll stick this in brackets still, 0.5421 minus 0.3388. And so what you get for a final answer is 0.1191. So that is the thing that we were after, ultimately. And this is much, much faster doing it this way than it would be if you tried to do it directly and, had to add up 14 probabilities to get it. Here, much less work, and I would say generally, if you have to get the probability of an inequality and it looks really long, just check. Just check to see if you use the complement, if you end up with something far shorter, because a lot of times that does work.